Pre-lab for the lab we're going to be doing over the next couple of weeks. It involves a two-step reaction sequence. And
in the real world, you don't do just one reaction. Syntheses are usually long sequences where you have some starting material and you take that and you do a reaction on it or a couple of reactions on it and you isolate a product. You take that product and then, as I mentioned, you use that product as your starting material in the next reaction to get your second product, and then you may repeat that process many times until you get to your final product. One of the things to note about multi-step syntheses is you calculate the yield at each step, and you'll see that the more steps you have in a synthesis, even if you have a 99% yield at every step, the more steps you have, that's going to decrease your overall yield of your final product. And some syntheses have very many steps. Here's a reaction we didn't get to talk about in class, or a compound we didn't get to talk about in class. This is a synthesis of a molecule called paleotoxin, which was published, I think, in the early 2000s, and this was 39 steps over 7 building blocks, and actually by the time you add up all the building blocks to synthesize all the steps, it was over 150 steps. So we're not going to do that.
rather than doing a 150-step synthesis, I think that we should start slow, and we will do what is essentially a two-step synthesis. The first step, this is what we're going to do next week. This is a reaction called a Friedel-Crafts acylation, and it is a version of an electrophilic aromatic substitution, similar to it's the same kind of reaction that we did last week in the nitration of methyl benzoate. And then once we isolate our product, what we'll do is we'll take that product on into the second step of the reaction and do something called a Grignard reaction. And that is a reaction that actually we will start talking about next week in class. So this week, as I said, you're going to be doing a Friedel-Crafts acylation. This is an example of a reaction called electrophilic aromatic substitution, or EAS. And as I mentioned in a second ago, it's the same as the nitration reaction that we did. And we will be discussing the mechanism of this in a few weeks. However, one of the intriguing parts, I think, about this reaction is, as you know, you have been assigned one of these alkyl benzenes as part of as one of your starting materials. And so what you have to do is you have to look at the NMR spectrum and determine which of these possible starting materials you have, because, well, once you determine the structure of your assigned compound, be sure to check with me for confirmation, and you'll need to look up things like the boiling point. You'll need to look up or calculate the molecular weight, and you have to calculate the mass of 0.03 moles, because that's the amount of material you're going to be starting with in the reaction. And notice, since they all have all the aromatic rings have different R groups on them, they obviously all have different masses, and so you're going to need to know what you have in order to know how much you're going to need to weigh out of the balance to do the reaction. You should also calculate other things like theoretical yield, and this is a 1-to-1. For every 1 mole of starting material, you get 1 mole of product, and this alkyl benzene is your limiting reagent. All the other reagents are present in excess. So here's your setup for the reaction mixture. It's obviously, since I've written it here 3 times with 6 exclamation points, it's really important that you keep this dry. This is a little bit different setup from what you've done before. It is very much like a reflux setup, which you've already done, but what we've done here is we've added in something called a Claisen adapter, and that basically gives us another inlet into the flasks. And the reason that we need that is because as this reaction mixture is reacting, we need to be able to add some reagents to it dropwise. Here's an example of what the apparatus is going to look like in real life. It's exactly the same. The only thing that is different is this week we won't be using the heating mantle, we'll just be using an ice bath. Also, in this, one of the things that's different from the drawing is here you can see the calcium chloride packed drying tubes that allow, they keep the reaction from being a closed system, but they also help dry out any air that might come into the reaction. So why does this have to be so dry? Well, both the aluminum chloride and the acetyl chloride are very water sensitive. Aluminum chloride reacts very violently with water, and so you need to be very careful with it as you're using it. The acetyl chloride, it smells bad, and it also reacts with water. And the way it reacts with water is, here is your acetyl chloride, and you'll notice here we go from having a chlorine attached to the carbonyl group to having an oxygen attached to the carbonyl group. So we go from acetyl chloride to acetic acid. And acetic acid is not a good acylating agent. And what that means when we say an acylating agent, we say it's not a good agent to add. This is an acyl group, so it's not a good agent to add that acyl group to the aromatic ring. And if you think about it, and you look at the difference between these two molecules, acetyl chloride has a Cl group here, as I mentioned, and acetic acid has an OH group here. And in order to make the acylating agent, those groups would have to leave. So when those groups leave, it would either be Cl minus or chloride ion or hydroxide ion. And chloride ion is a much, much better leaving group than hydroxide ion is. So that's why the acetic acid is not a good acylating agent. So keep it away from water so that it will be very reactive. Okay, before I take you through the procedure, just some hints to make sure that you are able to do this process efficiently. First off, really take some time to read the handout so that you have everything you're going to do planned out before you come in. It can be very helpful for you to talk with your lab partner and plan who's going to do what, who's going to do the setup, who's going to weigh things out, all that kind of stuff. Another thing that can help you save time in the organic lab, as I'm sure you are starting to understand, is you need to know when you need to be careful measuring and when you don't. For example, for your starting material, for your alkyl benzene, you need to be very, very careful measuring that because it's going to determine the theoretical yield. So you measure that carefully, it's on the balance. Acetyl chloride, that's present in excess. You're going to measure that with a graduated cylinder. You need to have about, I think it's 3.2 milliliters, but I'm not sure, but you know what the milliliters are. You'll be able to calculate that. So you don't have to worry about that quite as much. Now, it's when we're using solvents for the reaction and extraction, really, I mean, you just need to be, if it says 10 milliliters and it's somewhere between 9 and 11, that's fine. That's really okay. So, especially with extraction. So, you do not have to be as careful with that. And so, if you're spending a ton of time staring at a meniscus on a graduated cylinder trying to figure out if you have exactly 25 milliliters to do an extraction, you are wasting time that you could be doing other things. The aluminum chloride, because number one, it's present in a large excess, and number two, it's so reactive with water that will react with moisture in the atmosphere. You really want to measure that out very, very quickly and minimize exposure to air. Okay, so the first thing we're going to do, don't worry too much about the mechanism of this EAS reaction, but the first thing we need to do is we need to make this acylating agent. And that's when we have the acetyl chloride, and it reacts by the chloride ion leaving to make this positively charged molecule called an acylium ion. And so, like I said, we'll talk more about this mechanism, but we need to make that. So, what's the overall procedure we're going to go through? Well, here's your setup. Here's what you're going to have. And the first thing you want to do is you're going to add 6 grams, and notice it doesn't say 6.0, it just says 6 grams of the aluminum chloride to the round bottom flask. Then you're going to add the dichloromethane to the round bottom flask to in order to dissolve it. It won't dissolve, actually. It'll just kind of be a suspension. So once you have those two reagents mixed in the round bottom flask, then what we're going to do is we're going to add the acetyl chloride and then the dichloromethane to this thing right here, and that's called an addition funnel. And then notice the addition funnel has a stop clock so that you can add this mixture to the aluminum chloride solution. And as you add that, it's going to react, and you're going to see some color changes and things like that, which are really awesome to write in your notebook. But once you've added all of the acetyl chloride solution to the round bottom flask, you should have made your psyllium ion. Now, something I want to note here is that you can see that we have this in an ice water bath, and we have a reflux condenser on here. This reflux condenser in this reaction, it's really just in case, because, for example, the reaction is probably not going to reflux at all while you're doing this. It really shouldn't. However, if you slip and you say, add all this stuff at once, then it could be that the reaction would be sufficiently exothermic that it could start to reflux. And so, like I said, that's why we have the reflux condenser there. It's really just in case. Okay, so now that you have the psyllium ion down here ready to acylate your alkyl benzene, you can go ahead and dissolve that alkyl benzene that you've weighed out in your dichloromethane. And then what you're going to do is you're going to take this solution and put it into the addition funnel. There's your solution in the addition funnel. And then what you're going to do is add that solution dropwise over 10 minutes. And once again, this is going to stay at 0 degrees C because you've got an ice water bath, but you're going to add all of that. And then once you've added all of the alkyl benzene solution, then you can stir it for 15 minutes at room temperature. And hopefully at the end of all that, in the round bottom flask, you will have a solution of your acylated alkyl benzene, and this is also called generally an acetophenone. Alright, so once your reaction is done, then what you're going to do is you can not only remove the drying tubes, you can just take all of this stuff off. And what you can do is you're going to mix ice and 6 molar HCl in an Erlenmeyer, and then you're going to take the round bottom flask, and you're just going to pour it into that ice and hydrochloric acid mixture and allow that to stand for 10 minutes. And that will quench the reaction, and it will, at that point, you're going to have a mixture of your alkyl acetophenone and a whole lot of other stuff, and so we're going to need to work that up in order to get it away from the water and aluminum salts and all the other crap, chloride ions, all the other stuff that's in there. So this video is long enough, so stay tuned for the exciting conclusion, working up your reaction and isolating the product. Now, if you have any questions, Professor Dudley would like to remind you that you should be sure to ask them before you come to lab.